Hey, my name is Benjamin Völker, and I'm going to present you today joint work with my colleagues Mark Pfeiffer, Philipp Scholl, and Bernd Becker. We have developed the Smart Annotation tool specially designed for electricity data. We certainly agree that the development of non-intrusive load monitoring systems relies on the standard machine learning pipeline, which basically means that before a system is applied to live data, a suitable NILM model needs to be selected during an evaluation phase. During this phase, different NILM algorithms or parameter combinations are tested on pre-recorded data. This data is typically a dataset split into training and test data. To maintain reproducibility and comparability with works from other researchers, often publicly available datasets are used. Such an evaluation step can be performed, for example, with the NILM-TK framework. NILM-TK allows to compare different algorithms in a reproducible manner across different datasets. If we now take a closer look at those algorithms, we can roughly classify them into two groups. The first group are eventless NILM systems. These systems estimate the system state of all appliances for each time period of interest using, for example, hidden Markov models or neural networks. The second group are event-based systems. These divide the disaggregation step into three substeps. First, events are recognized in the aggregated load profile. Second, these events are classified, so basically they are related to their corresponding appliance. And third, the individual load profiles are reconstructed from the series of events and a priori knowledge. We can see that event-based systems can produce errors in each of the three steps. Moreover, if we want to evaluate each step individually, we require different ground truth data. The event detection process requires precise event timestamps. The classification step requires information about the event, like what was happening and which device caused the event. And the reconstruction step requires individual appliance profiles. If we look at some of the existing datasets, we can see that most only provide individual appliance profiles as the ground truth data. The blue dataset is the only one that provides event timestamps and event information, but therefore lack individual device profiles. Manually adding such information to existing datasets is a cumbersome and time-consuming process. First, you need to download the dataset to your system, and depending on the size of the dataset, this can require some preparation. The blonde dataset, for example, is as huge as 30 terabyte. Second, you need to develop code to load the dataset to memory, and this code is different for each dataset. This was also one of the drivers for the NILM-TK developers to agree to a standard storage format. Third, you need to develop a tool to present the data to the labeling person and get the user input, such as the marked events, back. Since there is no standard procedure or tool to do this, basically every research group interested in event-based NILM has to do this before they can actually apply their algorithms. We wanted to simplify the step and developed Annoticity. Annoticity is designed as an interactive web application and can be used to inspect and label electricity data. It allows the user to inspect different publicly available datasets or their own data. The tool allows to label the data either fully manually or via a semi-automatic labeling approach. You can add events and event labels to the data and download it in various file formats. The tool is split into a server backend and client frontend. The frontend allows for data selection, parameter selection, and adjusting of the labels. The backend handles data fetching, downsampling to improve visualization, automatic labeling, and serves file downloads. We currently support 5 publicly available datasets. Red is one of the first and mostly used dataset. UK-Dale is one of the longest datasets. The Eco dataset, the blonde dataset, is one of the datasets with the highest sampling rate. Again, there's the 30 terabyte datasets we talked about earlier. And the Fire dataset, which we introduced at the BuildSys conference this year. After selecting data, you can start adding labels manually, or by using the automatic labeling algorithm. The algorithm is split into 3 detectors: an event detector, a high variance filtering step, and a unique event identifier. The event detector is based on previous work and uses the log likelihood ratio test, which has been introduced by Pereira et al. It uses a sliding window and simple statistical features such as mean and variance to calculate the likelihood for an event to happen at sepal j. The resulting likelihood signal is afterwards cleaned and searched for local minima and maxima to detect the exact position of the event. The high variance filtering step removes recognized events in signal portions that show high variance. This avoids that appliances which change power rapidly, like a PC, for example, triggers too much false events. The unique event identifier tries to identify identical events to make it easier for the labeling person to add textual description to recurring events. It calculates the mean values between consecutive events because such a time period might actually represent a steady state of an appliance. The set of mean values is then clustered using hierarchical clustering, and a preliminary label is added to the found events. The user then only needs to change the textual description of one event, and for all other events, it's done automatically. We evaluated the event detector performance on the individual appliance recordings of 1 week of the red and 1 week of the fire dataset. To get a ground truth set for this evaluation, we added over 4,000 labels manually for these 2 weeks. To simplify the evaluation, we used the same parameters for each appliance in the data, but 2 different parameter sets for the different datasets due to different data resolution. We evaluated the results with some standard event detection metrics: true positives, false negatives, and F1 score. Summarized, we achieved a fairly good F1 score of 87% for the red dataset and 93% for the fire dataset. Better results for the fire dataset indicate that a higher temporal data resolution may improve event detection process. In particular, if we look at the results of similar appliances which are present in both datasets. But how can we relate these results to the benefit of Annoticity? Adding an accurate label to an event requires to zoom into the data, find the exact time of an event, and afterwards add the label. In contrast, visually inspecting automatically generated labels can be done much faster. You need to change the label's name and remove all false positive events. For a simple calculation, let's consider that adding a label requires 10 seconds, while removing a label only requires 5 seconds. Using a fully manual approach, adding the 4,000 labels of the evaluation would therefore have required over 11 hours. And indeed, I can tell you it was even more. If we would have used the automatic labeling, and let's recap, with a fixed parameter set for each appliance, the manual task would have been reduced to adding the missing 439 false negative labels and removing the 353 false positive labels. That's around 1 hour and 40 minutes, so an order of magnitude smaller compared to the fully manual approach. And that's not accounting for the aid which is provided for adding textual labels to these events. So let's come back to the NILM pipeline. As most datasets offer individual appliance profiles, it was already directly possible to evaluate eventless NILM systems and the last step of event-based NILM systems. Annoticity now can provide you with event timestamps and event labels. So you can use the timestamps to evaluate the event detector and the labels to evaluate the classification step. Let's summarize. Annoticity helps a lot when annotating time series data. And yes, you can upload any time series data to annotate it. The tool is not limited to electricity data. It's available for everyone as a web app hosted at our servers. And it gives you direct access to currently 5 publicly available datasets. And there will be more to come. For future work, we plan to support other file formats for download and upload of data, like for example HDF5 or plain CSV files. And we also plan to add other event detectors as well, so that you can choose the one that meets your requirements best.